This is your presenter Asloob Mudassar, and I am presenting slide number 80 of the course on laser physics. Question is, in a general laser system, a free space wave propagation region exists between the end mirrors where the wave propagation is well defined under Paraxial approximation. Considering two parallel planes separated by some distance, express the field at the output plane in terms of the field at the input plane, both in differential form and in integral form. The answer is, a monochromatic wave of frequency omega and amplitude E prime can be defined at a space coordinate x, y, z in the following form. That is, E as a function of x, y, z is equal to E prime as a function of x, y, z multiplied by e to the power iota omega t, where E prime of x, y, z is the spatial part of the wave. It must satisfy the Helmholtz equation, that is del square plus k square operating on E prime of x, y, z is equal to 0, as shown in equation number 2, where omega is equal to ck and k is equal to 2 pi over lambda. Let's assume that the wave travels from point P1 to P0 between two parallel planes separated by a distance capital L is equal to z minus z1. You can see that in this figure we have the two planes. One plane is situated at z is equal to z1. The other plane is at any other location z, which is separated from the previous plane by a distance capital L. Both planes are parallel to each other, so x1 axis and y1 axis are parallel to corresponding x and y axis respectively. R is actually the vector which connects the point P1 to the point P0. Capital L is the separation between the two planes. P1 is a general point on the input plane. Capital S is the surface area of the plane that we are considering, and P0 is the point of observation on a plane parallel to the input plane. Both planes are infinite in extent, that is, there are nothing that limits the dimensions of these planes. And the wave is incident on this area on the input plane, and from the input plane we want to calculate the contribution at the point P1, from the point P1 to the point P0, and then we shall calculate the total contribution over the surface capital S at the point of observation P0. The caption of the figure is geometry for field calculation from point P1 to P0. The x1, y1 plane is parallel to the xy plane and separated by a distance L, capital L, which is equal to z minus z1. Let's assume that the wave travels from point P1 to P0 between the two parallel planes separated by a distance capital L, which is equal to z minus z1. Under Paraxial approximation, the angle theta shown in figure number 1 is very small, such that cos of theta is equal to 1, and the field can be expressed as E prime of xyz is equal to u of xyz multiplied by e to the power minus iota kz. So you can see that the Paraxial approximation means that this theta angle is so small that we can approximate it as cos of theta is equal to 1. So this is referred to as the Paraxial approximation, and we are performing this calculation under the Paraxial approximation. And we have also written this equation number 3 under the Paraxial approximation, where we have assumed that the field u of xyz varies slowly along the z direction on a wavelength scale. So u travels very slowly from the plane z is equal to 1 to the plane z. and the phase factor e to the power iota kz takes care of the phase variation from the plane z1 to the plane z. U of xyz can be regarded as the paraxial wave approximation to the wave E prime of xyz. Substituting E prime xyz from equation number 3 into equation number 2. So this is equation number 3. We are substituting E prime from equation number 3 into equation number 2 and then operating it with del square and k square. The following equation is obtained, that is del square u minus 2 iota k and partial derivative of u with respect to z is equal to 0. This is equation number 4. This is the differential equation in the paraxial form of the Helmholtz equation, and its solution gives the wave u of xyz in paraxial form. The field distribution E prime of xyz is related to the field distribution E prime at the input plane x1, y1, z1, where z is the propagation distance through the Fresnel Kirchhoff integral formula. So we can relate the two fields, that is the field E prime at the z plane can be related to the field at the input plane z1, that is the z1 plane. The two fields can be correlated, can be related through the Fresnel Kirchhoff integral formula, which is given in equation number 5. So we have E prime of xyz on the left hand side, which is the field at the xyz plane, and that is equal to iota over lambda, and the double surface integral over the surface S of the field, which is the field E prime at x1, y1, z1 is the field at the prime P1 point, and the P1 point has the coordinate x1, y1 and z1. You can see this is the point P1. It has the coordinate x1, y1, z1. So we have the field at this point, which is in the integrand multiplied by e to the power iota kr over r multiplied by the cos of theta, and then we have the x1 and dy1, where r is actually the distance between the 2 points, that is the point P1 and the point P0, as you have also seen that we have shown in the figure r. So r is the distance between the 2 points, and which is given by x minus x1 whole square plus the square root of x minus x1 square plus y minus y1 square and plus z minus z1 square. This is r. And capital S is the area of the aperture, which also defines the limit of the integral. So you see that here the transparent region in the embedded in this opaque region is the area over which the integration will be performed, because this is the area S, and we want to calculate the contribution at point P0 due to the sources which are present in this surface area capital S. So this area capital S also defines the limits of the integral. So you see that in the integrand we can identify some terms. For example, E prime at xy at x1 y1 z1 multiplied by dx1 dy1 and multiplied by e to the power iota kr over r is the Huygens wavelet originating from the area element dx1 dy1 centered at the point P1. So we are considering a small area, an elemental area about the point P1 having dimension dx1 and dy1 over which the field E prime of x1, y1, z1 is assumed to be constant. So r is the factor that takes care of the amplitude while the field is propagated over the region r, and e to the power iota kr takes care of the phase variation from the point P1 to the point P0, and this whole terms is actually a spherical wave, you can say, originating from the point P1 and propagating towards the point P0, where E prime multiplied by dx1 dy1 divided by r is the amplitude of the spherical wave, and the phase of the spherical wave is e to the power minus iota kr. So the overall term can be regarded as the Huygens wavelet. The integral gives the sum of all Huygens wavelets contributing at the point P naught. So this integral actually takes care of all the Huygens wavelets in the area capital S, and we are actually, the integral actually sums up the contribution of all the Huygens wavelets from this area S at the point P naught, which is the point of observation. Cos of theta is referred to as the obliquity factor. Iota over lambda means that the Huygens wavelets are pi by 2 shifted compared to the beam incident at the aperture. So you see that we have not shown the beam and we have not discussed the beam which is incident on the input aperture placed at the location Z1. But the point P1 has undergone a phase change of a pi by 2 with respect to the field incident on this aperture. So that's why the term iota over lambda takes care of the phase. So iota over lambda means that the Huygens wavelets are pi by 2 shifted compared to the beam incident at the aperture. To write the integral under Paraxial wave approximation, we choose cos of theta equal to 1 and apply the Fresnel approximations. You see that cos of theta is equal to 1 is the Paraxial approximation. And in addition to that, we are applying the Fresnel approximations. The Fresnel approximations are given in red and blue. That is the mod value, that is the absolute value of x minus x1 is much less than z minus z1. And also the y minus the absolute value of y minus y1 is much less than z minus z1, which means that the area that we are considering on the input plane and the output plane, the dimensions of that area is much smaller in comparison with the separation between the two planes. That is the plane at z is equal to z1 and the plane at z is equal to z. So the dimensions of the area that we are considering, that is the area S, and the area that we are considering at the point P, they are very small in comparison with the separation between the two planes. This is actually the Fresnel approximation. The mathematical form of the Fresnel approximation has been represented in red and blue. And the physical meaning is what I have explained, that the dimensions of these areas are much smaller. That is the area of the input at the input plane and the area at the output plane are much smaller in comparison with the separation between the two planes. And then R takes the following form. So we can have R over here. We can expand R in the form that we can take Z minus Z1 to be common, because Z minus Z1 is a large quantity. We have taken it outside the square root, and then we have the terms within the square root, because you can see the power, that is 1 plus x minus x square plus y minus y square divided by z minus z square. This whole term and with the plus 1 has been raised to the power half, that is, this is a square root. Now you see that we can expand this term, and the expansion has been shown for only the two terms. And we have also multiplied the expansion with the term outside that one, which is z minus z1. So z minus z1 will multiply within the first two terms of the expansion, because we have ignored the third term and the other higher terms, because z minus z1 square is much greater than as compared with the dimensions x minus x square and y minus y square according to the Fresnel approximation. So the third term's contribution will be negligible. So our final value of R is given in equation number 6. The third term has been ignored, because you see that k e to the power iota kr, this is the term that we are encountering this term in the integral. And we have also using R in the expanded form as given in equation number 6. And you see that we have ignored the third term and higher terms. It is because k is a very large number, so and r is you see that the higher terms will be much smaller. So if you multiply k with r, then the result is that the third term is neglected, because the contribution of this term e to the power iota minus iota kr will be a small fraction of a radian. So due to this one, we have ignored the contribution of the third term, that is the r will be expanded only to the first two terms, because the third term's contribution due to this factor will be a small fraction of a radian. So that's why the third term and higher terms have been neglected. But you know that we have also r which is present in the denominator. Here we have no multiplication with k. So it means that here we in the r in the denominator, for the r in the denominator we cannot expand r, because we have to take care of all the terms in the expansion or the original form of r as given in over here. So we are not going to use r from equation number 6 in the denominator of the above integral. So r will be used only as r. But you see that in the term e to the power iota kr, we are using only the first two terms of the expansion as given in equation number 6. However, r is equal to z minus z1 will be used in the denominator of the function. Making these changes, the integral under Paraxial approximation takes the following form. So you see that we are now writing this integral as we have shown under the Paraxial approximation and also under the Fresnel approximations. And we get this integral, that is e prime at the xyz location is equal to, at the xyz point in principle, is equal to the iota into e to the power minus iota ka multiplied by z minus z1 divided by lambda, and also the factor z minus z1. And the integral over the surface area S contains e prime as a function of at the point x1 y1 z1 multiplied by e to the power minus iota kr, and the curly bracket contains only the two terms of the expansion in r, that is taken from equation number 6, and then we have e to the power minus iota k into, within the curly bracket we have x minus x1 square plus y minus y1 square divided by 2 into z minus z1. And then we have dx1 and dy1. This is known as the Huygen-Fresnel-Kirchhoff integral. You see that before that we have used the term Fresnel and Kirchhoff integral. That is over here. You will notice Fresnel-Kirchhoff integral for the equation number 5. Now we are adding another word, which is Huygen. So now we have the full name, that is the Huygen-Fresnel-Kirchhoff integral under Fresnel approximation. So substituting e prime as a function of x, y, z from equation number 3, that is from this equation, that is we are substituting this e prime in terms of the quantities on the right hand side, and after simplification we get this integral. Because these two expansions e to the power minus iota kz will be cancelled out by the term on the left hand side. So e to the power minus iota kz will also contribute from the left hand side. So these two phase factors will be cancelled out, and e to the power plus iota kz1 will be cancelled out by the contribution of the phase from this term, that is e prime of x1 y1 z1 when presented in the form of u of x1 y1 z1, and then the phase factor with this one will cancel out the phase factor with of e to the power minus iota k plus z1 will be cancelled out by this term. So the phase terms will be cancelled and we are left with this quantity. Here we are representing z minus z1 by the distance capital L. So we have now the form of the Huygen-Fresnel-Kirchhoff integral in the under the Fresnel approximation as given in equation number 8, that is u at the point x at the point p naught as a function of x, y, z is equal to iota over lambda into capital L, and the surface integral S is over the field U at the point x1, y1, z1 multiplied by e to the power iota, and within the curly bracket we have x minus x1 whole square plus y minus y1 whole square over 2L, and then we have the integration with respect to dx1 and dy1. So you see that this is the field, this is the integral of which we can use in order to calculate the field at the point P naught, that is the point of observation. So the field at the point of observation can be calculated due to the field present, due to the field contributions from this whole surface S. And we are using Paraxial approximations and the Fresnel approximations. This formula can be extended for a general optical system in the ABCD matrix elements, which requires no limiting apertures within the optical system, and that the optical components have infinitely large apertures. So you see that while we wrote down this integral, you see that we have the summation over the integral S, which in principle limits the dimensions of the integral, but you see that we have not specified the S. So if we assume that our input field, our input plane is of an infinite extent, and the output field is also of infinite extent, and if there are any optical components within these two planes, they will also be assumed to be of infinite extent, then we can write down the ABCD matrix form for this transformation of the field from the input plane to the output plane. So this formula can be extended for a general optical system in the ABCD matrix elements, which requires no limiting apertures within the optical system, and that the optical components have infinitely large apertures. Moreover, the optical system is contained between the two parallel planes located at z is equal to z1 and z is equal to z planes, and where the fields have been defined as u of x1, y1, z1 and u of x, y, z respectively, where u of x1, y1, z1 is the field at point P1 and u of x, y, z is the field at the point of observation P0 respectively. This is shown in figure number 2. The formula takes the following form. So you see that this is the formula, that this is the description that we have shown in order to calculate the ABCD matrix form of this formula. So you can see that we have the input field at the z is equal to z1 plane represented by u of x1, y1, z1, and at the output plane at a distance z is equal to z, we have the field there as u of x, y, z. So you see that you can see that we have these two planes shown in dotted. These two are the planes parallel to each other and contains a general optical system. And of course the separation between the two dotted planes is represented by capital L. The caption of the figure 2 is a general optical system between two parallel planes with fields indicated on each plane. Now you see that if we work out the ABCD form of for this figure with the help of this integral given in equation number 8, we shall come out with this formula, that is u at x, y, z is equal to iota over b into lambda, and the surface integral over S contains u of x1, y1, z1, and then we have the phase factor e to the power minus iota k, and within that one we have a curly bracket which contains a into x1 square plus y1 square plus d into x square plus y square minus 2x1 into x minus 2y1 into y divided by 2 capital B. And then the integration is with respect to dx1 and dy1. So this is equation number 9, and you see that this equation number 9 will help you to calculate the field at the output plane u of x, y, z when the input field is u of x1, y1, z1 containing a general optical system. The matrix element of that general optical system is represented by A, B, C and D. You see that capital C is not present over here. because capital C does not involve in the calculations of the field between the two planes. So capital C is equal to 0. This can be transformed for free space propagation under Paraxial approximation using capital A is equal to 1, capital D is equal to 1, capital B is equal to capital L, and capital C is equal to 0. So if you use these values of the matrix elements A, B, C and D in this formula, you will obtain this free space propagation formula, which we call Huygen Fresnel Kirchhoff integral form of the Fresnel formula for the field calculation between the two parallel planes separated by a distance capital L. So I think that the description is complete. So this is the end of slide number 80.